Hello class, today we will be discussing turbochargers. So what is the purpose of a turbo supercharger, or a turbocharger for short? The purpose of a turbocharger is to create a system that uses the same amount of displacement in an engine but produces more power, or to reduce displacement to achieve a power benchmark. An example could be this Porsche 911. Instead of using a inline six cylinder with a bigger engine, you can just use the same engine size and get more turbo power out of it. You can see here on these nice pictures I got from Google, the starting horsepower for a 2018 Porsche 911 is around 370 HP, whereas the turbocharged gains are over 100 horsepower just from adding that turbo. You can see mileage went down a little bit. It tends to do that. It's not ridiculous, but it does decrease the mileage you get out of your car by adding a turbo. So these are often used to replace a V6 or an inline six cylinder with a turbo V4 to end up producing more power with a smaller displacement. So a little background on an engine, if for anyone who's not super familiar, a four-stroke internal combustion engine is usually naturally aspirated, which just means the air going into the engine is naturally occurring. It's from the atmosphere. And then each of the four strokes you can see here are pretty well pictured in this picture, again, I got from Google. There's the first stroke, which is the intake, where the crankshaft rotates, the piston goes down, you take air in, and then you compress that air, you add the fuel into it, and then you combust it, then that piston goes back down, you then creating the power, and then the piston goes back up, sticking all that exhaust out, usually into the exhaust pipe. But those are the four main strokes of an engine that it's constantly doing while it's running. So how does this turbo help? Well, the exhaust coming out of that engine from that last stroke is essentially waste with momentum, so why not use that momentum? The gases spin a turbine that is on the same shaft as usually a centrifugal compressor that then compresses air to go back into the intake, that first stroke. And then if you can slam more air into it, there's also more fuel you can put into that air to combust and produce more power. So this diagram shows pretty well that whole process. Goes in the exhaust, out the exhaust after spinning the turbine, turbine spins, normal naturally aspirating air goes into the compressor, gets compressed into that air that goes into that first stroke. So charge density is just the technical term for the amount of air the engine can pull in. Like I said, more air, more fuel, higher charge density, more power produced, thus increasing the fuel combusting. The only other option to create more power normally, besides just tuning and having a more efficient system, is a bigger engine. So think like Mustang V8. The problem with this is they are heavier than a normal engine and more wasteful. So like if you have a stock V6, you want to increase it by, say, 150 horsepower. An option is to increase your engine size to a V8, add 2 more cylinders, add that amount of displacement, but then you've got to worry about more waste, and usually that metal is heavier, but usually the turbo just gets the job done a lot better. So there are some setbacks. Power increase from a turbo is relative to the exhausted gas flow. So at higher RPM, you're spitting out more gas, more exhaust, so then your power from the turbo is increased more. So it's not necessarily consistent across the whole range. You've got turbo lag. So like I said, you have to have exhaust before the turbo actually starts spinning. So there is some time that the engine is running without that exhaust powering the turbine up to its normal speed. So that time it takes to get there is called turbo lag. And there's also some increased stress that goes onto these engines. So engines are specifically designed to handle certain loads. So you should never just add a turbo to your engine. Lots of stress and parts could break, lots of stress could cause these parts to break, like these gears, shaft, bearings, because they're not used to these higher forces and loads, in addition to just being super tough to integrate into the first place. Well, like these turbos are a lot to work with. They're very complicated, and I'll get into a little bit later about the manufacturing process. But the only possible solution to ridiculous amounts of power that is actually harmful for the engine is something called a wastegate, and it's what it sounds like. It's just a little gate that lets out some of the air controlled by the system, usually your ECU, your engine control unit, and it'll let air out if it's producing too much power, so that less exhaust is powering the turbine and therefore producing less power. This is just purely for preventative measures and for safety reasons. So to go over the math a little bit, so we know that V is constant, right? That's the engine volume. That's what we're trying to keep constant to increase power. So P, the pressure, will go up because, like I said, we're shoving more air into the same volume. So that's what pressure is. That's how the turbo works. So we know V is constant. We know P goes up. And because of PV over T, that nice little gas law, T must also go up. So we know that heat transfer and pressure stresses, we can like see from this equation, we know definitely for a fact that they're going up and they're going to play a part. So some alternative uses outside of just your normal day-to-day car, high elevation aircraft. So in 1918, GE engineer Sanford Motts actually attached a turbocharger to a Liberty aircraft engine and tested it at Pikes Peak, which is about 14,000 feet above sea level. This test was to show that the turbo could compensate for power loss at high altitudes. High altitude means lower pressure. Lower pressure means less air and less fuel drawn into the engine, so it doesn't work as well. Kind of like the reverse problem a turbocharger solves. So the test proved its point successfully. The turbo successfully improved performance of the engine. And once the 1930s came around, turbos actually started regularly being used in all aircraft engines. Due to limits on fuel use and environmental reasons, these turbos are also used on Formula One cars and a lot of racing cars. So we don't want to let all these F1 teams just have bigger and bigger engines, because not only is that wasteful and contributing to a problem that's already bad enough, it keeps the competition a little closer if we mandate and limit engine size. So a way to get around that by being efficient, a way to be efficient by increasing power is to add a turbo. So you'll almost always see pretty much every F1 car nowadays have massive turbos. And another example, this is not necessarily an alternative use, it's a normal car, but the Bugatti Veyron actually has what's called a W16 engine. So imagine two V8s, two V's with your hand, just put those V's together, that's a W16. The V comes from like two V's, and then 16 because 8 plus 8 is 16. But each 4 cylinders on the Bugatti has its own turbocharger. So it's actually got what's called a quad turbo engine, which is what it sounds like. Quad for turbocharger. It's got a quad charged W16 engine. That's how it produces that over 1,000 horsepower that those monsters have. And it also needs a bunch of radiators. I think it has 11 or so radiators, whereas a normal car has 1, because it has to deal with all that heat that the engine produces. So that's another way that they're trying to, just produce maximum amounts of power. So some part specifics. In most automotive applications, the compressor and the turbine wheel are both radial. In some applications, such as diesel engines, they'll use axial flow turbines instead of radial, but that's a kind of niche product that I won't get into. You can kind of see how this works. Air comes in and radial blades get this turbine moving. The compressor starts compressing what's drawn in, and then it sends it to the engine. It's kind of got to deal with that perpendicular flow change. So the radial setup seemed to be the best. And this is just a nice little cross section of like a cutout of an actual system. You can see the turbine on the right and the shaft that it's connected to with the compressor on the left. So to get into the specifics of the blades themselves, the compressor blades are usually made with castings just because they're easy to produce in high volume. You make one, you have one process, and you can kind of just keep doing it, and it's a very easy process to put on a mass scale. So this, you can also billet them, which is kind of a much more in-depth way of doing this, and it's kind of only for stronger parts in low quantities. So like these F1 cars might have billeted turbos, and same with some planes, since obviously there are quite a few more cars than planes out there. These planes might use billeting processes as opposed to castings, and also due to the sheer size. But the reason like the billets are so much more expensive is because you have to use a 5-axis milling machine, and you have to use it's for special low volume, high durability, high performance applications where production wheels can't really fit the intended need. Additionally, you can see here that it's got that pretty flat face at the top. That's called the nose. And then the other side, that's the bottom in this picture, is called the back face. Because the blades in the shaft and the turbochargers rotate at such high speeds, dynamic balance is critical for correct operation and the lifespan of the part. So the wheel is set up on specially designed balance machines with these two planes of balance defined, and a balance spec is met by the manufacturer based on the turbo size and intended operational speed. So typically the balance spec is held within a few hundredths of an ounce-inch, so these are pretty precise. On very, very high speed applications, the rotor group can be dynamically balanced by stacking up all of the components that rotate and indexing them, then balancing them all as a group, because the group is kind of more important than the individual at that point. So that's more of a specific situation that I don't need to cover, just sort of a fun fact. Onto the turbine. So the turbine is definitely the heart of the turbocharger. It's what extracts all the energy from the exhaust to drive the compressor in the first place. It has two main components, the wheel and the shaft assembly. So the shaft assembly is technically a separate part, but it's usually treated as one part as a whole. Manufacturers don't really sell turbine, wheel, and shaft components separately because the manner of assembly is not really possible for an average person. In aircraft applications, it actually is made to be one part, just as a fail-safe dictated by the FAA. In all other applications, they're just welded together. But the turbine wheel is definitely the most critical component. It's also the most costly component because of how much design goes into it and how much, it's got to be casted and mass manufactured. It's the heart of the component, so the most effort gets put into it. It's usually made from materials that can tolerate heat really well because, this air literally had exploding gas in it, and now it's spinning a turbine, so that's got a lot of energy. It's really, really hot air, so this metal has to be able to handle that. So these metals are usually really tolerant of high heat and contain a lot of nickel, more often than not. But the shaft itself has to obviously deal with a lot of power. So if you're starting at 370 horsepower on this turbo or on this stock Porsche 911, and then trying to get up to about 540 horsepower with this turbo, you can't just kind of have any old shaft with any old threads. And I'm getting into this just because of my last internship. I worked with fasteners, obviously have threads, so I kind of know a decent amount about this, so it's kind of cool to make a connection between the two. So these turbine applications will use rolled threads instead of cut threads, which creates a stronger shaft once torqued with the compressor. The reason that it's stronger is because the grain structure is retained. You can kind of see from these pictures a pretty simple and clear image. Cut threads obviously interrupt the grain structure, which impedes strength, and it makes it a lot less strong, whereas rolling the threads compresses the grain structure and makes the thread stronger because that structure is retained, and that structure is really what gives metal their inherent strength. In commonplace applications, screws will be cut because it's a lot easier and cheaper and provides sufficient strength anyway, such that rolling isn't really necessary. Like, think about like the screws that hold together a grill that you got from IKEA, right? Those aren't dealing with super high loads of 540 horsepower, spinning at thousands of RPM. Like, that's just a screw you put in to hold the handle on the top of the grill. Like, very different scenarios, but that's why these turbine shafts will use super high strength rolled threaded shafts. So the housings are pretty much just kind of designed around the blades for each specific application. The housings aren't super critical. The design that goes into them is kind of just like fitted around the turbine and the compressor, just kind of make something that works. It doesn't have to be perfect, just literally make something that covers everything fine. So the housings are designed around the wheel to fit into an engine for a specific application. One turbine can have many, many, many different possible housing solutions. Again, it's just a very simple, it needs to kind of cover the whole thing. So a lot of what we've done in class, especially recently, has been with axial turbines, whereas these are radial turbines. These are also one of the only applications where these radial designs are used. These designs are somewhat similar to like low-speed Francis turbines. The triangles look somewhat similar, the velocity triangles, but the blades are usually shaped such that the absolute velocity is directed axially. Looking at the Euler equation, you can see the work clearly increases with high values of inlet tangential velocity or absolute velocity, and with smaller values of the inlet relative velocity. This radial design helps like accomplish this so that you can maximize your work. So applying some other math and stuff from class, here's the equation for pressure ratio, the ideal outlet temperature, the adiabatic efficiency. So you can see on this nice graph, it's very straightforward. So you've got your blue line, that first one, the leftmost, that's what your ideal compressor looks like. Quasi-ideal means like realistically what we have, what's probably the maximum we'll ever get to. And then you've got your less ideal, your realistic scenario, where your entropy is obviously increasing greatly. But this just helps with efficiency calculations. So that adiabatic efficiency usually is about 0.4 to 0.8. 80% is probably the best you're going to get, and that's going to take a lot of design and R&D. Just some quick calcs. Here's the power. So 1 over that efficiency times mass flow rate times the specific work gives you the power, and that specific work ideally is right here down below. You can see it takes into account our stagnation temperature, your outlet temperature, or not stagnation, your original temperature. So that's one important thing, is this T0 and P0 aren't stagnation temperature and pressure. They're just your original, like your baseline temperature, and then P1 is your outlet. So this characteristic map shows the typical increase by an exhaust gas turbocharger. This uses a 1.5 liter engine specifically for like this picture. You can kind of see that the torque is about 35-ish% peak torque above where it was, and it's pretty constant increase over the entire range as opposed to the horsepower. You can see that the horsepower has a little bit of an increase down about 1,000 revs, but once you get up to like 4,000, it's way higher. And like I said, that's due to the amount of airflow going in. Kind of makes sense. I discussed why that happens. And it increases kind of like, it looks like about a 40% increase. But you can see here quantitatively how this turbocharged engine has increased performance characteristics compared to a naturally aspirated engine. So to kind of recap everything, just go over the advantages and disadvantages of the system. Turbochargers have increased efficiency for a constant volume. That's what they're for, is to create equal or more power from the same or lesser displacement. You have increased overall torque and power output values, so you can go faster, quicker. You have constant torque over an operating range, and constant torque is a very good thing to have because, you know, change is harder to deal with, so constant torque is very nice. Lower emissions for a given power output compared to a larger naturally aspirated engine with the same power rating. So like I said, if you just need an engine, it just needs to have, you know, 500 horsepower. This is going to have lower emissions with like a turbo V6 as opposed to a naturally aspirated V8. So that's good. It helps you go faster, and it also helps the environment and all that good stuff. So some disadvantages of turbochargers, though, because there are a few, it adds a lot of complexity to the system as well as weight and cost. So like I said, this is a very complex system. Manufacturers don't even think about letting you guys take care of this stuff on your own. They do all of it ahead of time because of how complex it is. It does add a little weight to the car. It is a little heavier, and obviously these cost more. More R&D, more integration into an existing engine. Makes sense. Like I said, turbo lag. So turbo lag can be something that's tricky to deal with. Lower mechanical efficiency. Like I said, this puts a lot more stress on engine components. So if you were to take, you know, just like your normal Honda engine, like I had in high school, and throw a turbo on there, a lot of the parts in your engine would probably fail because of how much stress it puts on. So it does decrease the mechanical efficiency of all your parts. And there's also an increased risk of knocking. If you don't know what knocking is, it's just a premature combustion of the compressed air to fuel mixture due to the higher compression ratios. So here are some of my references. Google for all images. Use this website to put some nice definitions together. And I also used Professor Canova's 5427 Lecture 24 from spring of 2015, and he also cited these references. So thank you for watching.